All right, well, today we want to talk about double replacement reactions, precipitation reactions, as well as acid base double replacement reactions. So, first of all, when you have a precipitation reaction, you'll have two soluble ionic compounds that are reacting. And then you're going to get a product that is insoluble, which is called the precipitate. So, the first thing you do, you have your two reactants. Well, this is the one type of reaction where the charges don't change. There's no oxidation reduction like the other reactions. So if I know what the charges are over here, they'll be the same in my products. So nitrate we know is -1, and there's two of them in this compound. So that tells us the lead is +2. So since lead is a transition metal, you have to figure out its charge based on what it's with. So we know the lead is +2, the nitrate's -1, potassium's always +1, chlorine is -1. So I'm going to switch the two positive ions. And so the K, which is +1, is going to go with NO3, which is -1. So I just need one of each of those. And then the PB, which is +2, is going to go with the Cl, which is -1. So I'm going to need two Cls. Okay, so first I balance my charges to make my products. Then I balance the equation overall. So I'll need a 2 here for the two nitrates on that side and a 2 here for the two Ks. And then I also have two Cls and one lead on both sides. So there's my balanced equation for the double replacement. Now, one of those two products is a precipitate. And remember, you have to know the solubility rules. And one of the solubility rules is that nitrates are always soluble. So that is not the precipitate. Another rule, very common, is that alkali metal ions are always soluble. So both of those, this is not the precipitate. So that means this one is the precipitate. And some of the solubility rules, you know that lead is always a compound that is often in a precipitate. So lead chloride is not soluble. So S is for solid. So S is not soluble. S is solid. So there's my precipitate. Okay, so that's called the molecular equation when everything is written as a molecule, even when it's an ionic compound, it's really a formula unit, but it's all written together. But we need to then write the net ionic equation. In AP, the molecular equation is not going to get you any points if it's a one that you can split up into ions and give a net ionic equation. So again, if we had PB NO3 2 plus KCl, and I get PbCl2 plus KNO3. If that's my molecular, 2 here, 2 here, and this was my precipitate. Now, anything that is aqueous, which these were solutions, so they're aqueous ionic compounds. That means that they really don't exist like that. They, in solution, will be split up into ions. So the Pb is +2, and there's 2 nitrate ions. So this is how they really are. These two ions, they don't exist all together as a formula unit or molecule. And then this one will split up into 2 K pluses. So the 2 applies to the K and it applies to the Cl minus. Now, ions must have charges. Okay, ions must have charges. There's a big difference between nitrate, which is NO3 -1, and nitrogen trioxide, which is a gas, just NO3. So if you just wrote NO3 here, that is not the same thing. This is nitrate, the ion. Lead +2 in this ionic compound is different than just Pb, which is solid lead. And the solid lead is losing 2 electrons to become stable. So Pb +2 is more stable. That's the ion. So you have to have the charge on the ion. Now over here, what doesn't split up is the precipitate. So PbCl2 does not split apart. That's the only thing in this ionic equation that stays together. So then the two Ks come out as K plus, and the two nitrates are also split up. So this first one is your molecular equation. This one is the complete or total ionic equation. When you split everything into ions, that is aqueous ionic compounds, except for the precipitate. The precipitate doesn't split up. So now I'm going to change color. I look and see what's exactly the same on both sides. There's two K pluses on both sides. There is two NO3 minuses on both sides. Those will cancel out. So what do I have left is Pb plus 2 plus 2Cl minus, making PbCl2. This is your net ionic equation. And in AP, that's the only thing that matters. If you were told that lead 2 nitrate solution was mixed with a potassium chloride solution, what's the equation for that? This is what we want, just the net ionic equation. Okay, so you need to have the, I usually write the molecular first. I often don't write the complete ionic because once I know what the precipitate is, the net ionic is just the ions making the precipitate. So from this compound here, the precipitate, once I write that, I know what the net ionic is going to be. If you want to write the complete ionic, then you should write the complete ionic and do your cancellation. But most of the time, no one's going to ask you for the total ionic or the complete ionic. Everybody wants the net ionic. So if you can just look at what the precipitate will be, then the ions that make the precipitate, that's the net ionic. Okay. An acid-base reaction is also a double replacement reaction. They can also be called neutralization reactions because what happens when we add an acid and a base? They neutralize each other exactly if they're exactly the same moles of each. But at any rate, in this one, we have a strong acid with a strong base. So just like other double replacements, we have a plus ion with a minus ion, plus ion with a minus ion. So when the pluses change places, the H is going to go with the OH. We get HOH, which is water. And then the Na is going to go with the Cl. Okay, so we had a plus with a plus with a minus. Now, in this case, we're not making a precipitate, we're making water, which is a pure liquid. So that's like a precipitate, it doesn't break up. So pure liquids and solids and gases do not break up into ions. So this water that's formed is not going to break apart. But the HCl, being a strong acid, breaks up into H plus and Cl minus. The NaOH is a strong base, but it's also a soluble ionic compound. It breaks up into Na plus and OH minus. Then the water does not break apart, but NaCl is soluble. It's got an alkali metal in it. So Na plus and Cl minus are the result. So now I can cancel off the Na pluses and the Cl minuses. And what I have left is the net ionic equation. H plus OH minus makes water. Now this is the net ionic equation for every strong acid, strong base, aqueous solution mixture. Okay, so as long as they're aqueous and they're strong acid, strong base, this will always be the net ionic equation. So in another example, right here, I have sulfuric acid and KOH. I don't even have to go any further because I recognize that this is one of the 6 strong acids. This is one of the strong bases. So I can just jump right to the net ionic equation. For every strong acid mixed with strong base, aqueous solutions, This is the net ionic equation. Okay, so sulfuric acid and KOH, that's the reaction. So if it's a strong acid and a strong base. Now, if it's a base that is a solid, like potassium carbonate, you don't break solids up into ions. So in this one, you're still going to get the H going with the base part. So this is a plus ion, this is a minus ion, this is a plus, this is a minus. But I'm going to have the calcium nitrate formed, and I'm going to get H2CO3 formed. So I'm not going to get water in this one. I'm going to get this carbonic acid. However, carbonic acid immediately breaks down to form water and CO2. So I do get water formed. It's just that in a double replacement, first the carbonic acid is formed, but then it breaks down to form water and CO2. And then this calcium carbonate is a solid, so it doesn't break up, but this would break up. And actually, we would need a 2 here to balance this. And so the calcium carbonate does not break up because it's a solid. The strong acid aqueous breaks up. Calcium nitrate would be soluble, and if this is aqueous, we know that it's in water, so there's water around. So this would break up also. And then we have our water and CO2. So the nitrate will cancel, and that is it. So for this one, the net ionic equation would be solid calcium carbonate plus, sorry, it's kind of messy. Let me rewrite that. So solid calcium carbonate plus 2H plus 2NO3 minus goes to Ca plus 2 plus H2O plus CO2. So that would be the net ionic equation when the acid is solid, or when the base is solid. Okay, it would work the same if the acid was a weak acid that was solid. But in this case, the base is solid, the acid is aqueous, so this doesn't all split up into ions, so we don't end up with H plus OH minus makes water in this case. So if it's an aqueous strong acid, an aqueous strong base, we will always get H plus OH minus makes water. But in this case, I didn't have that. Okay. So in reactions, strong acids are just written as H plus, and then you can write the other ion just to show, but it'll cancel out. So the 6 strong acids, once again, you must know those: HCl, HBr, HI, HNO3, H2SO4, and perchloric HClO4. Those were just written as H plus, and then the anion usually cancels out, but if you're writing it, it'll have the minus charge. Every other acid is a weak acid, and those do not split apart in ionic equations. So if it's acetic acid or hydrofluoric acid, any of those other acids, if it's H with something else and it's a weak acid, you have to leave it together as a molecule in the equations. But all the strong bases also split up into ions in water. So NaOH will split up. And the strong bases are your alkali metals with OH and your larger alkaline earth metals with OH, with a hydroxide. So like calcium hydroxide, strontium hydroxide, barium hydroxide, and all the alkali metals with hydroxide. Those are your strong bases. Those will split up as long as they're in water. You have to have water to have ions. If it's a solid base, it does not split apart on the reactant side if it says it's solid and it's not aqueous. And then again, here's our strong bases. So NaOH, aqueous, is really Na plus and OH minus in water. The most common weak base is ammonia, and ammonia is not going to be written as ions either. Ammonia, NH3, will stay together as ammonia. It won't be broken apart. There's other weak bases that are called amines. They're a form of ammonia. So a nitrogen group with carbon groups on instead of hydrogens, those are amines. Same thing. Those are stay together as a molecule in reactions. All right, but soluble ionic compounds, strong acids, strong bases, if they're aqueous, you must split them up into ions. And then if water is a product, it doesn't split apart. If there's a precipitate for a product, it doesn't split apart. You should be able to now write the molecular equation, the complete ionic equation, and most importantly, the net ionic equation.